Hello, everyone. Welcome back to part two of reading schematics. I conveniently call this one the deeper dive schematics for sophomores for non-EEs. So before I get going, just a reminder that any questions you have as I'm doing this presentation, please put them on slido.com #chromium. We are on track C. Okay, let's get rolling. So if you're here for my first talk, a schematic like this, which seemed pretty intimidating at first, now is digestible. You have the patterns that you need in order to be able to read this. But there's so much more that we use in our schematics, right? These are just a few of the examples that I put on here. I'm not going to go over them. If you want to figure them out, I would recommend talking to a EE friend, and they accept payment in all kinds of stuff, beer or candy or champagne, depending on the season. Okay, and really, what I'm going to focus on today is a little bit more about these magic blocks that we can see here. Stuff like that. What is that? And they have really long part numbers on them. Well, this stuff is logic, digital logic to be precise. And this is part of the 7400 series logic, which was created way before I was born and cost a lot of money. Nowadays, these things sell for dirt cheap. And the beauty of the 7400 series logic is that they have a standard pin configuration, and they are all numbered. So with the number, you can tell a lot about what's inside. So for example, this is the 7400-00. This is a quad 2-input NAND gate, so not and. So anytime you see a schematic with 7400, you know that you've got yourself a logic chip that has 4 2-input NAND gates. And the insides are kind of custom for every vendor. Every vendor will do a die and they'll lay it out their own way. To us, it doesn't matter. What we care about is how the pins are mapped. And at the end of the day, you can build quite a bit with that. In fact, basic logic chips like this is what made Apollo fly. This is a shot of the lunar vehicle, the launch vehicle computer, sorry. And the schematic is open source and public, should you be interested in seeing it. But it's a lot of logic gates. And if you look closely, this isn't quite a NAND gate. This is actually a NOR gate. So the NOR gate 7400 series number is 7402. We have the quad 2-input NOR gate. And NASA kind of did it their own way. They didn't really use a 7400 series part. They wanted a 3-input NOR gate, and they wanted to be have slightly different behavior. And they made their own custom die for it, and they packaged it in their own way. But ultimately, it's the same idea. And a little bit of computer engineering, you can build a full computer with any logic function as long as it accepts more than one input and the output is invertible. But I digress. Okay, there's a whole series of logic families, and we use a splattering of these in our Chromebooks. Really, the important thing here is that AND gates kind of have this rounded rectangle shape to it. OR gates kind of have that arrow, and the buffer or the NOT gate is just a flat out triangle. And whenever you have the negative of the logic function, we'll add a little circle at the end. So AND NAND or NOR. This is exclusive OR, and this is exclusive NOR, etc. And as I said, every one of these logic functions has a 7400 series part number associated with it. And just looking at this quickly, we have the quad 2-input NAND gate, but we also have the quad 2-input NAND gate as an open collector, which is synonym for open drain. We talked about that in our last talk. There's a 6 inverter logic chip, right? There's a triple 3-input NAND gate, etc. And as the years went by, the 74 series kind of expanded and it went beyond simple logic and started doing a lot more complicated logic. So we have really fun part numbers like serial to parallel interfaces or 32-bit ALUs or the 64-bit barrel shifter. I particularly like this one, a JTAG concatenator. How many times have you had to concatenate your JTAGs? But something kind of interesting here is that you notice that every single one of these parts has an X here. So 74X 8838. But over here, I have a whole bunch of text between those two, LV, ACT, AS. What's going on? Well, remember I was talking about how the insides doesn't really matter to us. What matters is the pinout. Well, it sort of matters in that we can use different types of transistors to implement the logic functions or the function of the chip. In the early days, we used BJTs. This is before we had MOSFETs. So we have a whole family of 7400 series that use BJTs, and they use different kinds of BJTs in different configurations. But that is all but obsolete. We don't use BJTs anymore. They consume too much power. So we've moved on to MOSFETs, and the family for MOSFETs is much more vast. You can ignore almost all of these because almost every design I've seen on Earth uses any one of these highlighted. The LVC one is particularly common. And really what it boils down to is every single family is done a little differently on the inside. So this is how a 7400 LS schematic would look like for 2 inputs and 1 output. And an HC would use MOSFETs instead. And I didn't draw the 2 input here because I ran out of real estate. The important thing to note here is that all of these ICs, irrespective of how they're made on the insides, have a power connection and a ground connection on the bottom. So back to a schematic, you can see here, this is our AND gate. Great. And it has the power and ground connection. So now you know that the AND gate will use 3.3 volts, and that's what it's going to output out here. So it'll take the AND of these 2 wires and output 0 or 3.3 volts, depending on the logic. And the part number is here. It's 74 LVDC, so we know it's the LVC family. And then the numbers after that is 1G08. The 08 is our AND gate, so this would be a quad 2-input AND gate. But what's this 1G here? Well, a normal quad 2-input AND gate has a lot of pins. And sometimes we don't really need all 4 gates. And frankly, we don't have a lot of space for extra pins that we don't use. So later in life, the 74 series got kind of amended the family and added the 1G family, which is a 1-gate version of the otherwise 4-gate version that you would have normally. So the part number has the 1G appended to it. And this is a small example with a 6-pin part. There's also a 2G sometimes version. So you might see 74 LVC 2G08, and that would tell you, okay, this is 2 AND gates. And this matters a lot, the 1 gate, because we can make them really small. And small means saving space, and saving space means saving cost, and also being able to put more stuff in the same area. Okay, so another example, we have the NOT gate down here, and here are our power and ground connection. We know, okay, great. So this is a 3.3 volt, and now you can kind of get a sense of, we have this AND gate, and then it goes to the NOT gate, and it gets inverted. Neat. Part number, 74 LVC 1G04, right? The 7404 is our hex inverter that I kind of highlighted earlier. And the 1G means that we have only 1 of these in a single chip as opposed to 4. So I don't know if you noticed, but every single one of these logic chips has a capacitor tied to ground hanging near it. Now, why is that? So let's talk about decoupling capacitors. I've taken the structure of a 74 HC CMOS logic chip, and I'm going to remove all the extra cruft. We're just going to look at the transistors and the inputs and outputs. So suppose I connect my two transistors here to an inverter on this end. Well, this really translates to a resistor and a capacitor to ground. So from the point of view of these two MOSFETs, they will see going into the inverter a resistor and a capacitor to ground. And this makes sense because if there's a resistor on the input in our structure for how we make our logic chip, the next one will have that resistor too. But this capacitor actually has to do with the fact that MOSFETs are not perfect ideal devices, and they have these things called parasitics. So a MOSFET will have these capacitors. We don't put them in, it's just a result of how we make the transistor. So we'll have capacitors from the gate to the drain, from the gate to the source, and there's also a drain to source capacitance. And this capacitance is part of that RC that we're seeing that was shown on the previous slide. The actual model is much more complicated. I won't get into it. Just know that it's not as, the parasitics are much more involved. Anyway, all that to say that we have an R and we have a C as the output. And from the previous talk, I was talking about the step response of a RC circuit, the low pass filter, right? We start with a voltage that rises progressively over time, and the current starts really high and decreases progressively over time. So suppose we have this situation and we are putting a lot of energy into the RC. At first, we have a large current and our voltage will slowly rise. And over time, as the voltage is rising, the current going into that path will slow down. But that's not the entire story, because our electrons that power this RC have to come from somewhere. So I just drew in a battery here, but from the previous talk, you know that the battery is plugged into a connector. So energy has to come from the battery through the connector and make its way all the way to our power source. And that's a long way, at least electrically speaking. It's a very long way. So the electrons, as they travel, they take time. And what we model that long path as is a parasitic inductance. And I haven't talked about inductors and a parasitic resistance. But really the point is, inductors and resistors aside, it takes a finite amount of time for the electrons to go from the battery all the way to our two MOSFETs here. So when you end up with a situation like this, you will see that as we have this large current coming in that needs to feed this RC circuit, there's not enough electrons here to actually properly fill this up at the speed that it wants to. And you'll end up with a voltage that starts to dip. And because of our parasitic inductance, I won't get into much of that, you don't get just a dip, you get a squiggle. So this is a diagram showing that, you know, if we have this sharp rise on our digital signal, if you were to probe the output on your oscilloscope, you would see that you would get a finite rise, and then this kind of wiggles around until it finally settles. And sometimes that's okay. Like it's not a problem, we don't care. But a lot of times, and especially as signals get faster, this oscillation gets larger. And at some point, you don't have a digital signal anymore. You just have a bunch of noise. Oh, I had nice arrows to point all that out. Okay, so when we add these capacitors, it's a little battery close to the logic chip, so that when we have this immediate low to high response, all the electrons that are missing can be fed right from that capacitor right there. And then the battery has more time to fill the capacitor again. Okay, so we've talked about logic gates, we've talked about decoupling. Now we know that the logic gates and the capacitors kind of go together. All these make sense. You AND two signals, you OR two signals, you XOR two signals. You NOT it. But a buffer, why a buffer? You take A and you get the exact same thing on the other side. It seems like not a super useful piece of logic. And if you look at our schematics, we use these everywhere. There's a buffer here, there's a buffer here, there's a buffer here. What's going on? Well, we have a lot of reasons to use buffers. And frankly, in half an hour, I don't have enough time to talk about all the reasons for this, but I'll focus on really two. I'll do a non-inverting open drain example and a Schmidt trigger input. If you want to learn about the other stuff, again, beers or champagne go a long way. Okay, so we're gonna start with the inverter circuit that we talked about in the previous class. I won't go into the details of how this works. If you weren't present for the previous class, just once this is over, go and listen to it, and this will make a lot of sense. So suppose I wanted to not have this circuit be an inverter. Well, what I could do is put two inverters back to back. All right. One of the downsides here is that no matter what I do, I'm going to be consuming electricity either via this path or this path. And that sometimes is unacceptable. Sometimes we want to save energy when we can. So we will use something called a non-inverting open drain circuit. And the key here is this little symbol. So we have a buffer, but it's amended with a little symbol. And this symbol is part of the IEEE standard 91 symbols, and it's the open collector symbol, also known as the open drain. We used to call them open collectors because of the early days of 7400 series logic that used BJTs, but we use those terms interchangeably now. Anyways, open collector, open drain, kind of the same idea. So we have this buffer, and it's an open drain buffer. I'm going to use our inverter circuit. I'm going to simplify it a little bit, and I'm going to add a NOT gate, a NOT logic chip here to make it not invert. And this actually transforms into this circuit here, and I'm going to show you how this works. So suppose that my power is 3.3 volts, and I give it a logic 1 or 3.3 volts on the input. We've talked about MOSFETs in the previous lecture, and we know that when the gate to source voltage is above a certain point, our resistance starts to decrease. So we're going to have a discharge path from the gate all the way to ground. And that turns that MOSFET off. So our output would be 1. And here it doesn't really make sense what 1 means because there's nothing connected here. So I'm going to add a resistor. Okay, now this resistor is pulled to 1.8 volt for the MMC supply in our S0 power domain. Great. Now my 1 means a 1.8 volts. Okay, so far so good. So given a 1, I get a 1, right? So that's the non-inverting portion here. And it's worth noting that I give it a 3.3 volts and I got 1.8 on my output. So this is definitely non-inverting and level shifting. All right, now if I give it a 0, we have, surprise, surprise, a PFET. I haven't talked about PFETs yet. So far, all the arrows have been pointing from the center of the MOSFET towards the gate. But this one's pointing the other way, which tells us this is a PFET. And the two lines connecting together show us our source. This is, again, from the previous class. So now we know that we have our gate, our drain, our source. We can figure out that hasn't changed. And really, PFETs are exactly the same thing as NFETs. The only difference is that the resistance decreases as the gate to source voltage becomes more negative as opposed to more positive. That is the only difference. How they're made is slightly different, but I won't get into those details. So really, as our gate to source voltage decreases, our resistance from the drain to source converges to 0 ohms. So for example, if I have a gate to source of 0 volts, I could expect a resistance of, say, 1 mega ohm. And if I have a negative 3.3, I could expect the resistance to be something like 4 ohms. So with that in mind, let's see what happens here. we have, oh, sorry, too fast. We have 3.3 volts here and 0 volts here. So our gate to source is 0 minus 3.3 or negative 3.3. So we'll call the RDS on 4 ohms. This turns on, oh, that I screwed up the animation there. Okay. Well, anyways, ignore this red line here for now. This turns on the transistor, and so the energy comes from our power source and hits the gate here. So our gate will be 3.3 volts, which turns on our transistor here, which is an N-channel transistor, right? Because the gate to source voltage is now 3.3. And this is, again, just our classic inverter circuit from that we've had in the previous class. So our output now will be 0 volts. So given, oh geez, I really screwed up the animation here. So given 0 volts, we have 0 volts on the output. So effectively, this is what we're doing. We're just doing level shifting, right, from 1.8 to 3.3. And we're doing it in a non-inverting way. The distinction here is that whereas we could do it with 2 inverting transistors, as I've shown before, this will only consume energy when the output is driven to 0 volts. When the output is not, this circuit won't consume any power. And we use this property to save battery power, because saving battery power sells Chromebooks. So that's the non-inverting open drain circuit. But if you look closely, there's another symbol here. That's not the open drain symbol. This is some squiggly thing. This is referred to as a Schmidt trigger. This is another type of buffer we use quite a bit. Really, the Schmidt trigger makes sense when you look at what happens downstream from our logic circuit that we just kind of talked about. So this is, again, the same circuit we had before. And suppose that I'm tying my output to another gate, and I just picked something, it doesn't matter. The point is that we end up with another RC input. And effectively, what happens is when the signal needs to charge this parasitic capacitance from the MOSFET, we have a low-pass filter here of sorts. So it takes time. So what you'll see is that the signal will rise slowly over time. And then when you need to discharge, it happens very quickly. But you get this ramp, so to speak. And sometimes that's not a problem. In fact, most times that's not a problem. But sometimes we have really fast signals, and this rise is too slow. So what the Schmidt trigger does is it takes a slow rise, or incidentally a slow fall if we had one, and turns them into nice, sharp up and downs. And that's exactly what this symbol means. So when you see the symbol, it's like, okay, this is meant to clean up a signal to make it go up and down faster. All right. So with this knowledge, let's look at this circuit. This is the kind of circuit that from last class, we can kind of break it down, right? We have an inverting level shifter here. We have an inverting level shifter here. And now with our newfound knowledge, we know, this is an open drain buffer, and it's the 1 gate version, and this is the part number. Okay, great. Yes, oh yeah, the level shift here from 1.8 to 3.3 volts. And our decoupling, lest we forget. So we can actually take it a step further here. I'm going to say that this is actually a NOR gate, and I'm going to prove this to you. So if I break this down as I have 2 inputs, X, Y, and an output Z, we use the exact same rules we've used for the inverting circuit, right? If we give it zeros, we know that we get a 1, or in this case, it would be 3.3 volts. And as you walk this, you start to build your logic table, and lo and behold, this logic function here is not OR. Pretty neat. So now we were able to take 2 building blocks that we learned before and combine them. We can take this a step further. Suppose that now that I know this is an and not or. I can look at the entire circuit and say, I have inputs A, B, C, and then output Y. I can build this logic table here where if B or C are 1, I get a 0 on the output always. Otherwise, the output tracks the input. So if I have a 0 on A, the output is, if I have a 0 on A, the output Y is A. And if I have 1, I get a 1. So this is actually pretty neat. We're able to take a circuit that we don't really have a ton of understanding on and understand its behavior very in a very detailed way. And let's not forget, we also level shifted the thing too, which is pretty cool. So hopefully this was able to show you that we have these building blocks. We don't necessarily need to know all of them to get a good sense of how to start reading these schematics. And we've barely scratched the surface here. So if you have any doubts or questions, this is a good opportunity to ask a friend or just pick up a book and start learning. At the end of the day, we're not launching anything into space here. We're just making laptops. All right. Let's see if we have any questions. All right, I'll hold off for like a minute or so. Give folks some time to conjure up questions, and if there's nothing, then we'll just call it a few minutes early. All right, I guess we'll call it. Again, thank you for your time. I think I'm the last session of the day, so congratulations for surviving Chrome University. And we'll see you next time.